All right, so if you're watching this on the video, which I guess you are because you're listening to me, what I've done is I've uploaded the portion that dealt with linearly increasing loads. I'm going to move on now to internal releases. When I upload the PDF of the notes themselves, they're all going to be together, right? But the videos are sort of broken up so you can sort of take them in little snippets and hopefully refresh your attention span there. So right now, the last issue that we sort of have to deal with moment diagrams is what do we do with internal releases? So a quick discussion of what a release is, right? So a release is a continuity condition that basically eliminates the ability for the structure to transfer a specific action, right? So the ones that we are going to deal with is a moment release, right? And that means that there can be no moment at the location of the release. Right. So basically you've put a hinge, people use a hinge, sort of like everybody's kind of familiar with how doors open and close. That hinge can't provide any resistance to moment. In fact, it wouldn't work if it did, because then you couldn't open the door. And so in some cases, we actually put things that behave similar to those hinges within our structures. There's a number of reasons for why and how we do that. I will tell you that primarily it's a cost issue. So let me just give you an example of a very common type of hinge that is in a structure. So if this is a column, right? So if I were actually to flip it up, it would look something like this, right? So those lines are actually the flanges of the column. And in a lot of cases, and you can see this in Weeks Hall if we ever get back to campus this semester, they shop weld here what they call a shear tab, right? And that shear tab has a number of holes in it, right, to receive bolts. And then the beam frames in. So the beam frames in something like this, right? And again, this is intended to be an I section. This really is just for steel structures, but that's probably a fairly connection that you've seen if you've bothered to try to look at structures. It's a very common connection type. And in general, you might look at that and say, well, there's 3 holes there, so that can transfer moment between the beam and the column. And the answer to that is, of course, yes, there's some moment that's transferred, but for all intents and purposes, the moment that can be transferred is almost 0. And the reason is, as you recall when we were doing the flexural response of beams, that actually the flanges are where all the moment is carried, right? In fact, that's why we put flanges on there. We're pushing that area away from the neutral axis. So all of the moment stress is actually taken by these flanges. And if you notice, this connection does not connect the flanges of the beam, where the moment is, to the flanges of the column, which have the ability to resist moment as well. And because those things are not connected, it's the moment at this location is for all intents and purposes 0. And so we would model this as a hinge. And that is a very common assumption. If there's some minor moment transfer, maybe 1% to 5% of what it would be if it was a fully continuous connection, then that's just a little bit extra conservatism that we have in our design. Now, if you want to create a connection, a good connection, let's say, between a steel beam and a column, there's a number of ways to do it, but in some way you have to connect the flanges of the beam to the flanges of the girder, because that's where the moment wants to flow through, right? So if that's not done, and again, it's not done primarily for cost reasons, those connections are just a lot more expensive. And so we end up building structures, I wouldn't say with a huge number of releases, but certainly steel structures are generally built with some releases. Whereas reinforced concrete structures, the cost isn't that big of a deal. Most of the time with concrete structures, you tend to find more continuous connections. In either case, understanding how to deal with releases is really important. So let's do a quick example here. And there's really only one rule on how to deal with releases. So if I'm going to draw a structure with a release, and the release we're just going to draw as a little circle there, and the difference between that and the roller support is the roller support has this little hashed area underneath it. So the one common misconception with a moment release is a lot of people just assume that there's a reaction there, right? There is no reaction at that internal hinge, right? There's no support there. So there's nothing external to the beam that is stopping that hinge from moving up or down, right? So I am going to load this with a uniformly distributed load, right? And we will call that uniformly distributed load W. And I think I called this A, B, and C, like that. And okay, so then I have to dimension this, so I will do that. So this guy is L, and that guy is L as well, right? And so this is our hinge, right, which is a moment release. Hinge, which I'm going to call it a moment release. And the reason I use both of these terms, hinge is commonly used, sort of in discussions with people. Moment release is the term that a lot of softwares incorporate. So if you're running structural analysis package and you want to put a hinge in, you are not going to generally find the ability to do that. You're going to have to apply a moment release, because that's really what it is. So let me see where my notes are. Okay, so let me do this. So the first rule, and really the only thing that makes this different, right? So this is the only change, is you must break up the structure at the release first, and second, you must replace the release with equal and opposite forces that the release can transfer. Okay, so what do I mean by that? Right. Well, you'll see it in the example here. But if I have a moment release, so let me just draw this moment release, right? What that becomes is what that becomes is now I've separated the structure, right? And I'm going to put the two forces that moment release can transfer, right? So they can transfer horizontal force and vertical force, cannot transfer moment, right? And then on the opposite side, I'm going to put the equal and opposite forces, right? So these guys here are equal and opposite. Right? So what does that mean? It means that if the red beam is pushing up on the green beam, then the green beam is pushing down on the red beam the exact same amount. Right? There's no there's no way equilibrium can be satisfied if that's not true. Right? Okay, so let's do this problem. Right? So the first thing we're going to do is we're going to break it up at the hinge. Right? So we have about like that, and about like that. So this guy is my support. My support is here, and then this is my distributed load. See, I'm going to extend this a little. Like that. Right, so this guy is L, and this guy is also L, and this guy is W. Right? So I don't care really about the sign convention here. You know, you can choose one or the other. You know, it doesn't really matter. So here I'm going to apply the axial forces next to one, you know, pointing at one another, and I'm going to apply my vertical forces in that direction. So this we're going to call QY. We're going to call this QX. So Q is really an internal action, right? So this becomes QX, and this becomes QY. Again, there's only two unknowns here, because as soon as I solve for QY and QX, let's say the left-hand portion of the structure, I'm just going to flip it over and apply it to the right-hand portion of the structure, and vice versa, right? So then I will, here I guess in red, I can also apply my my reactions. So this is, I guess we'll call this RAY, we'll call this RAX, and we'll call this RAZ, like that, okay? And then this guy here, we will call this RCY, like that, okay? All right, so now we've set it up. Hopefully, you know, that doesn't seem, I've written W twice, hopefully that doesn't seem too challenging. But what I want you to do is now look at this structure and see sort of two structures, right? I have this structure here, right? And then I have, I'll do it in black, I guess. And then I have that structure there, right? So if I look at the structure that's circled in green, what you see is I only have three unknowns, right? I have RCY, right? I have QY, and I have QX, right? So I can apply equilibrium, and I can solve for the QX and QY, right? And then when I'm done solving for QX and QY, then I can dump QX and QY in over here, right? And then I can solve for RAY, RAX, and RAZ, right? And that's exactly how these problems are solved. So we first break it up, then we choose the side of the structure to address. All right, once we've broken it up, equilibrium has to apply to both sides of the structure. So actually we have 6 equilibrium equations here. And if you count up the unknowns, we have 6, right? RCY is 1. Right, actually, let me count them this way. So that's 1, 2, 3. This is 4, 5. This is 5, 4, because they're exactly the same. And then RCY is 6, right? 6 equations, 6 unknowns, I can solve, right? So let's do, we're going to take the right-hand side first, right? So I am going to apply this fictitious load of WL, right? And that load is applied at L over 2, right? And so here I get, let's see, some of the moments in the, I guess we'll do this about point Q here, equals 0. And what I solve for now is that RCY, well, let me actually do this. So we'll get a minus WL times WL over 2, because that's right-hand rule into the board, and I will get a plus RCY times L, and that equals 0. And when I solve for RCY, I end up with, where is it, WL over 2, and that is vertically upwards. So I will box that in red, that's really important. Then I can sum forces in the y direction. They have to equal 0. So here I'm going to get a positive WL over 2, that's my R sub y. I'm going to get a minus WL, that's my distributed load, and I'm going to get a positive Q sub y. And for that, Q sub y is going to be again a positive WL over 2, and so that is upwards. And the key here is that this is upwards on right-hand member. Because obviously it's downward on the left-hand member, right? So we look at the left-hand member, and the way you think about this is the left-hand member is holding up the right-hand member. So the right-hand member is pulling down on the left-hand member, the left-hand member is pulling up on the right-hand member. Okay. And we will then simply do, this is just for completeness. Hopefully nobody gets confused about this, but you can see that QX has to be 0, right? And actually, just looking at this, you could observe that QX actually has to be 0. Right? Okay, so that is that. So now let's move on to the left-hand side, right? So here what I'm going to do is, I guess we can sum moments about A. That has to equal 0, right? So that's about the left-hand support, right? And now what I'm going to get is a minus QY times L, and I'm going to get a positive RAZ, right? And that QAY is actually WL over 2, right? And when you solve for then your RAZ, you end up with WL squared over 2. And I'm going to draw that in this direction, right? That is not a positive internal moment, right? This is a reaction, so this is a positive external moment, right? It is drawn as compression on the bottom, if you see the way the arrow is drawn, right? So that's going to be important when it comes time to drawing our moment in shear diagrams, which is of course the entire point of this. And if we sort of finish this up here, we can do some of the forces in the y direction, right? That has to equal 0. what you will see is that RAY equals WL over 2. That's upwards. And you can also do some of the forces in the x direction has to equal 0. And there you will get RAX equals 0. Again, that's a little trivial because we just don't have any loads in that direction. Right? So those are our important reactions, right? So now we've sort of resolved the entire structure. The way that I would say it is, now no matter where I make a cut in the structure, I can figure out what the internal forces are, right? And that's really what we need to do, because we want to ultimately solve for our moment diagram, right? So the next step is we're going to redraw the structure with all of the reactions and forces at the releases, right? So what does that look like? So let me draw this guy, looks like that, and this guy looks like that. So here, we've got our structure on the right, and then on the left we've got this guy here, WL over 2, WL squared over 2. This is the force down, which is QY, that's WL over 2. This is my QY force up on the left-hand member, right? And this is my reaction RCY. Clean that up a little bit. So this is WL over 2 like that, and this is W like that, right? So you can make your cuts wherever you want, right? Because again, we have all of our forces. So here what I'm going to do is I'm going to decide to make a cut from right to left there, and I'm going to decide to make a cut from left to right on the right hand side. And just so we're all clear about where these are, these points are both B, right? That release happens at a tiny location, right? So now I just make my cut. Ooh, let me turn on that. So I'm going to make this cut and add this force and dimension this guy. So this is x1. This is moment of x1 and shear of x1. Again, those follow our local sign conventions, right? So our local sign convention, we've defined it before. That's why we put the shear force up when it's on the left-hand side. Moment is always compression on the top, right? So if we sum moments about the cut like that, we will get that I get a minus m of x1 minus WL over 2, x1 equals 0, and my m of x1 is minus WL over 2 times x1. And then if you sum forces in the y direction, and that equals 0, then you will get a v of x1 equals WL over 2. And here I will just box these. So that's the moment diagram for the left-hand portion of the structure. And this guy is the moment diagram for the right-hand portion of the structure. And now we can, let me just draw a line in between here so you see we're separating it here. Now we're going to apply the same thing to the right, now. So I'm making my cut. And again, you could just as easily define this from left to right if you want. You know, you go ahead and do it, and you should get exactly the same results. If you don't, then you know we gotta talk, because it shouldn't matter. All right, so this guy is my x2. This force is WL over 2. Right. So now I apply my little green, you know, fictitious load, which is W times x2. And that acts at a distance of x2 over 2, like that. Okay, last thing is I've got to apply my my internal forces, right, according to their local sign convention, right? Again, so we're back to that. Now, if you're on the right-hand side of the member, shear force is down. Moment always causes compression on the top of the beam. So now we can sum moments about the cut, and that has to equal 0. So again, the cut is here, and when we do that guy, we get a minus WL over 2 times x1. So that's the moment caused by the WL over 2 at the left-hand side. We get a positive WX2. I'm sorry, this should be x2. We get a WX2. That's the total amount of distributed load that's on here. And its moment arm is x2 over 2. And then we get a moment of x2, which is our internal force there. And so our m of x2 is this guy here, which is just WL over 2 times x2 minus WX squared, x2 squared over 2. So I'm going to box that guy. And almost done here. So now we can sum forces in the y direction. And if you do that, you are going to get WL over 2 minus WX2. And I will box that in red. So these guys here are our moment and shear diagrams, right, for the structure with the release, right? The release rule is you break it up. When you break it up, you basically turned a single problem into two problems, right? How are they linked? They're linked because these guys are equal and opposite forces, right? That's how they're linked, right? So we choose one, we solve for those internal forces, the actions at the release. We then flip them over and apply them to the other side of the structure, right? That's why it's not two completely separate problems, right? Okay. So last part of this guy is to actually do the plotting, right? So let me go ahead and redraw the structure here. And this guy is a fixed support, and this guy is a roller support. And this guy here is our distributed load. Right. This guy here is L and omega, right? So now what I'm going to do is I'm going to draw the forces here, or my reactions, in red. So the vertical reaction at the left-hand side is WL over 2. Vertical reaction at the right-hand side is WL over 2. And then the moment reaction at the left-hand side is WL squared over 2, and that's causing compression on the bottom, right? And one thing I want to do, just to sort of accentuate this, and I'll do it in pink, is that the hinge forces are in this direction, right? So this is WL over 2, and this guy is WL over 2, right? So what this is intended to show is the right-hand side of the member feels like it's being pushed upwards at its left-hand side. And the left-hand member feels like it's being pulled downward at its right-hand side, right? So that's the direction that these forces are. And the last thing I've got to show here is the X1 and X2, right? So we'll do, I guess we'll do shear force this time in blue, right? So if we go back and we look here, the shear force on the left-hand side is a positive WL over 2. Right? So that's just there. Positive WL over 2. And then if we look here, the shear force is WL over 2 minus WX2. So when X2 is 0, it's just WL over 2. When X2 is L, it's minus WL over 2. And so that guy looks like this. And that should look somewhat familiar to you, right? So this guy is WL over 2 minus WX2, right? And this guy is just WL over 2, right? And the value here is minus WL over 2, like that. Good? So the fact that I have no distributed load on the left-hand part, that means my shear is constant, right? I have a uniformly distributed load on the right-hand part, that means my shear varies linearly, right? So always one order above. Okay, so now the last one, maybe slightly more interesting than the others, looks like this. Alright, so then this is a support here. This is a support like that. So if I look at the left-hand side, right, we're here. So at x1 equals L, which remember x1 is from right to left, right, on that member. So at x1 equals L, that's the support. We're at minus WL squared over 2, right, so that's going to be somewhere here. And then it varies linearly, and when x1 equals 0, the moment is 0. Right? So this guy does something like that. Where this value here is minus WL squared over 2, right? And that should make some sense because it is exactly the same as the reaction, which it has to be. Right? And the value here is minus WL x1 over 2, right? Which is exactly that guy there, right? And just a reminder, right? My x1 is taken from the right-hand side of the beam. Right? Now, on the right-hand end of the left-hand beam. So now if we look at the right-hand member, this is our moment diagram. That should look really familiar to you. That's the parabola, the simply supported beam that has a uniformly distributed load, right? And so if we're going to draw it, it actually looks something like this. Let me try to do a slightly better job. Let's say 3, 3, okay. So something like that. And so this equation here is just my WL over 2 x2 minus WX2 squared over 2. If I've made a mistake somewhere with these x2s and x1s, just understand x2 is only valid for the right-hand member, x1 is only valid for the left-hand member, right? So if I'm talking about a left-hand or the right-hand member, that should be the x1s and x2s sort of respectively, right? And this guy here is WL squared over 8, right? So that's the maximum value, right? So a couple things to note, and we'll make a bigger deal about this in the next lecture where I sort of go through what I'll call a cheat sheet here, is if we look here, again, left to right, don't look at the equations, because our x1 is taken from right to left, which is, sort of flips the signs. But if we look at the shear diagram here, right, it's a positive WL over 2. And if we look at the slope of the moment diagram in that region, it is also a positive WL over 2, right? And then we can see this is linearly varying downward for the right-hand member. That is the slope of the moment diagram. So here, if I were to sort of create a line like that for the 0 slope, that's where the moment diagram is a maximum, right? So one question that you might want to ponder is, what happens at this hinge, right? It's certainly a 0 moment, we know that, right? We sort of enforced it with our, not sort of, we absolutely enforced it with our equilibrium, but you can see the moment diagram crosses 0. But is the slope on the left-hand side of the moment release exactly the same as the slope on the right-hand side of the moment release? Right? So think about that. We can chat about that, I guess, tomorrow in class. That's it for